When I started the work, I planned on styling this video like one from Adrian's digital basement. I'd film an intro before the work ever began, and then I'll video myself working, and then edit it all together. Life had its own ideas, however, and that didn't come to pass. So instead, I'm filming this after everything works. I'd still like to show you what I did and how it panned out. I won't go into all the nitty-gritty details, just some of them. So, without further ado, let's get right to it. One design decision I'm really proud of is the overall structure. The CompuSAR display is made of two completely separate graphic interfaces, one for the 32-bit computer and one for the 8-bit computer. Each fetches the memory, calculates pixels, and prepares them for display completely independently. At the very end, there is a component called display aggregator that fetches the two pixel sources and merges into one pixel color, which is then sent to the actual HDMI encoder. Particularly crucial here is the interface between the two graphic processors and the aggregator. The three need to be synchronized so that pixels don't move around the screen. The standard way is to send a sync signal that indicates start of display, and then have each interface keep track of where it is on screen. I found this design to be too complex to do correctly. Instead, I'm using my standard synchronous interface to pass pixels around. Here's a quick recap, and we'll focus on write operation as that's the only ones where the interfaces do. When a bus master, so the CPU for example, wants to write to memory, there are two crucial pieces of information. These are the data to be written and the address where to write it. So far, fairly obvious. With a synchronous interface, however, it also needs to tell when those two are valid. The precise names used for that vary somewhat, so my naming convention may not be what you see others use. This when is signaled using two bits. One, called valid, comes from the master. It indicates that the address and data values are what should actually be written, as opposed to some random junk that happened to be there. This allows cycles where the data does not need to be written. This is unlike the 6502's asynchronous bus, for instance, where each cycle it needs to perform a memory operation whether it needs the data or not. The second signal, which I call ACK, comes from the bus slave. It indicates that the slave device is ready to perform a bus operation. This allows devices with different inherent speed to talk to each other. So when our RISC-V, running at 75 MHz, wants to send a byte over UART, running at 115,200 baud, so able to accept data at 11 kilobyte per second, this is the mechanism that ensures that data isn't lost. The UART is able to lower its ACK signal until it can handle a new byte, thus slowing the CPU down. This mechanism is often referred to as back pressure. Regular viewers may remember that this is how I ran the Apple CPU at 1 MHz, despite the CPU itself working with a 75 MHz clock. The mechanism for the display aggregator is the same with a few differences. The first is that instead of data and address, what we pass here is pixel color and XY coordinate. The coordinates are not random access. The graphics interface must provide them in the same order in which they need to be displayed. But the interface is allowed to skip ahead. So if the Apple II's display only needs a frame that is 280 pixels wide and 192 pixels tall, and needs to display it on a canvas that is 640 pixels wide and 480 pixels tall, it only needs to provide those pixels it actually wants to paint. When it finishes a row, it can skip ahead to the beginning of the next row. The way this works is that the aggregator gets the pixel information and holds onto it until it's time to display it. If the time is now, it immediately sends it out. If the time has not yet come, it lowers the ACK signal. This causes the interface to halt its own pipeline, filling it up if it's not already saturated. The beauty of this is that each interface need only generate its own pixel information, It needn't worry about the pixels it's not displaying, nor does it need to worry whether the same pixel is also displayed by the other interface. More importantly, no pixel is displayed out of place while keeping the logic simple. Simpler. Simplish.
Apple II display memory.
What I was trying to do is to get the Apple II to display text mode on HDMI. The first Apple II text page is located at address hex 400, but the layout is not as straightforward as one might expect. The first 40 bytes of memory are the first line of text, which we'll call line 0. This is at addresses 400 to 427. For clarity, these 40 bytes translate to 40 characters on screen at an unsurprising 1 byte per character. The second 40 bytes, at addresses 428 through 44F, however, contain line 8, or a third of the screen down. Continuing this trend, the next 40 bytes, at addresses 450 through 477, are for line 16, another third of the screen down. Next come 8 bytes that are not displayed on the screen at all, because obviously we have lots of memory to spare. The next 40 bytes, starting at 480, are finally for line 1, followed by line 9, 17, and 8 more bytes that are not displayed anywhere. This pattern repeats until we finally get the whole screen. 40 columns, 24 rows, and 64 bytes that are skipped over. There was a claim that this was done because it allowed combining the memory refresh with the display. It sounds reasonable, but when I try to look up the datasheets, the numbers fail to add up. It seems that the memory needs a refresh every 2 milliseconds, whereas at 60 Hz display and going over all memory rows every third of a screen, we only refresh the rows every 5.5 milliseconds. If anyone knows more, please let me know in the comments. As a display interface, we also need to keep track of which line we're at inside the character row. Each character representation is stored in a character ROM. These store their visual representation of a character as 8 bytes, of which the top bit of each byte is not used. So aside from this scan, we also need to keep an internal counter of which character line we're on. The one upside to this weird scheme is this. It's the same scheme for all Apple II display modes. Yup, all of them. The standard modes include these modes. 40-column display. That's what we've just seen. Low-res graphics. This is just the same scan as the 40-column text mode, except each byte read provides 4 bits to the top pixel block and 4 bits to the bottom pixel block. This means we scan the display at exactly the same way, and we use the character line counter to determine whether we use the top nibble or the bottom one. High-res graphics. The starting address is different, which doesn't matter. The first 40 bytes provide the first line. The second moves a third of the screen down, followed by another third down and 8 unused bytes. We then return not to line 1, as we have in text mode, but to line 8. We repeat this pattern until we update 24 lines. Only then, at offset 400 from the base address, do we paint line 1, and the pattern continues with a 1-line offset. At first, this scan seems completely different and definitely more complicated. On second glance, however, we notice that the first 400 bytes, i.e., the size of the text page, scan the exact same way and at the exact same pixel locations as the text page. The second 400 bytes repeat the process 1 line down and so on. So all we have to do is take the character line counter and multiply it by hex 400, and we have the address to fetch data from. The exact same scan with the exact same counters. Next comes the 80-column text mode, double low-res and double high-res. Here, too, little changes. The only difference is that where before we used to fetch 1 byte from main memory, now we do 2 fetches from the same address, one from main memory and one from auxiliary. We display the screen interleaving bytes, one from auxiliary, one from main.
Implementing the display.
So now we need to implement the logic to replicate this weird scan. Thankfully, most of it is not as complicated as it first looks, though, admittedly, it took me a while to see it. All we need is a line counter counting from 0 to 191. Of this counter, the lower 3 bits are the character line counter, the next 3 bits are the line counter, and the next 2 the thirds counter. We can now isolate each counter and calculate the address accordingly, where, except the thirds counter, each bits of a counter turn into bits of address in a one-to-one relationship. For the thirds counter, I'm using a third bias register that increments by 40 each time we finish a third. And that's it. We turn a pixel location to a fetch address.
Character ROM.
The original Apple II used a character ROM to convert the byte value to pixels on screen. For our system, using a ROM, i.e. read-only memory, makes no sense. So instead, we use RAM and initialize it with software running on the 32-bit computer. The source of the data is from the original character ROMs. We use the same technique we used for the Apple II ROM to load it into the ELF. We then initialize all the relevant parameters. These include copying the character font, as well as initializing display mode, location of the characters in memory, and where to display it all on the screen. We then reset a bit in our internal GPIO. This is just a generic input-output control for the RISC, but is connected to the reset lines of various devices on the Apple side. So when we do that, the 8-bit display is taken out of reset and begins fetching bytes and displaying pixels.
It freaking works.
I know some people have a huge emotional reaction when things finally click.
Oh, look, it freaking works. It freaking works.
I usually don't. I start out with a very clear picture of what I want to do and how it'll pan out. And while it rarely, if ever, works on the first try, I typically have a fairly accurate mental picture of how high I am on the ladder leading to the end. As a result, when things finally pan out, it feels more like a small step than a huge leap. I have no idea why, but this time was different. To start, a lot of things went wrong. From forgetting to latch on the right edge of the clock through a lot of small miswiring and other problems. The simulation were, as usual, a huge help, but it was actually a synthesis attempt that caught the major problem. When I solved those, I loaded the design and got this. Now, granted, it's not exactly what you'd call fully working, but still, we're seeing here the characters from the font displayed on the HDMI display. This was a huge deal to me and it resulted in sending excited messages to anyone who might even remotely care. I even sent a teaser to my Patreon supporters. Of course, this still shows two obvious problems. The first is that the characters are mirrored. When going over the various character ROMs, it was obvious some saved the leftmost pixel in the least significant bit of the byte, while others saved it in bit 6. Since the Apple II's CPU cannot read the character ROM, it doesn't really matter which one is used, so instead of fixing the hardware, I reversed the bits as part of the compile and link process. This led to this image. The second obvious problem is that we should have seen a different image. What I know, however, is that this pattern isn't random. When the system starts, I'm seeding the memory with a certain pattern. The pattern on screen is consistent with the pattern I'm seeding the memory with. This, combined with the fact I know the Apple II was booting before, means that the Apple CPU never gets around to running. On a hunch, I checked the code with which I'm taking the Apple out of reset, and sure enough, the register I'm using for resetting bits at the GPIO had a tiny bug. A very quick fix later, and it freaking works. I mean, the commit message even says so. And I'm sorry, I refuse to feign that excitement in retrospect. You'll have to believe me, it was there when it happened.
Unsquishing the display. As I may have mentioned once or twice already, the Apple II display is 40 columns and 24 rows of text, with each character being 7 pixels wide and 8 pixels high. That amounts to 6 plus 3, 280 over 192 pixels. If we just display it as is in a 640 over 480 display, that'll look like this. Obviously, that's not ideal, and the solution is fairly straightforward. Just draw each pixel as a 2x2 grid. As a side note, doubling the pixels horizontally isn't even optional. While we might get away with not doing it for text mode, we cannot properly display the graphic modes at 280 pixels wide. Yes, even the non-double ones, but that's a story for another time. Doubling the pixels horizontally is fairly straightforward. We just generate 14 pixels for each byte we read instead of 7. Doubling vertically, however, poses a somewhat bigger challenge. The problem is that we must produce the pixels in the order in which they are displayed. While we can skip unused areas of the screen, we cannot jump back. This means that we pretty much have to finish displaying the line once and then regenerate the same pixels again for a second line, all while not maintaining a frame buffer. My first solution was to just bump the display y coordinate by 2 instead of by 1. This means all pixels are displayed with more or less correct aspect ratio, but there are black lines between the lines. I call this the scanlines solution because you might be able to sell it by saying it emulates NTSC scanlines. And while for white on black text it even kind of works, the trouble is that once we employ inverse text, the illusion breaks down. It is fairly obvious that these are black lines, not scanlines. Option number 2 is the one I call interlace. It comes from understanding how the original display worked.
The original display updates the screen 60 times a second, or 59.97 if you're inclined for pedantic accuracy, but it does not, in fact, update the whole display every time. Instead, on the first scan, it updates just the even lines, and then it updates just the odd ones. Or maybe it was the other way around. I can't seem to care enough to remember which. So while the screen does get a refresh 60 times a second, each line is only updated 30 times a second. The slight misalignment between the runs are what scanlines actually are.
Implementing this is absurdly simple. I just keep track of which frame it is and bump the starting point by 1 line on every other frame. I doubt the video encoder used by YouTube is able to capture the result in a way that does it justice. It looks kinda bad, but it's a very good kinda bad. For fixed text, there is hardly any flicker, as 30 FPS is still high enough. Even better, now the eye does catches that there are black lines between the pixels, but it cannot quite place where they actually are. As a result, this does look quite a lot like NTSC scanlines. All in all, this is a fairly accurate emulation of how an actual CRT display would look. But there are downsides. While it looks cool, it isn't very comfortable to look at. I think I'll keep it around, but only as a gimmick.
Which brings us to the obvious solution. Reread the same line twice. It's not a horrible solution, and I did, in fact, implement just that. But I'm not a huge fan of it, for a reason that frankly isn't very good, which is this. It's not how the original Apple II did it. All other solutions read the same address and just as frequently as an original Apple II. With that said, with modern hardware, this is a minor problem at best, so there's just what we'll go with, at least for now. So there you have it. Display is working, there's lots more to do on the display. In particular, I need to add the graphic modes, color, and AD column, but all of those will wait for now. I want to build a foundation in other areas before I come back here. So Until next time, thank you for watching.